to today talk about our progress in terms of Internet of Things. And I'm going to talk about the architecture design, the simulation studies we have already had, and also the ongoing implementation work that we had in terms of supporting Internet of Things. So I think in order to talk about Internet of Things, the first question people always ask me is, can you tell me what is Internet of Things? Well, that's actually a very hard question. So I'm not going to, usually if I give a talk, the first sentence I say is, well, I want to introduce what Internet Things, what is Internet Things. I actually do not have a very clear answer at the beginning. So, but hopefully, throughout this talk, after all the discussions, that definition can come together at the end. Let's see. So let's start with the requirements. A lot of times we don't know what a thing is, but we actually know what requirements this thing have. So Internet of Things, we put together a IRTF draft on the requirements of Internet of Things. So I'm not going to go through with all the list because all of these everybody knows, but I'm going to pick one or two and just to illustrate. For instance, naming. Why is naming challenging? For everyone who has done any work with respect to sensors and sensor networks, and naming a sensor is really easy, right? You either use its manufacturer ID, or you use it's a temperature sensor, or you use it based upon its location. It's a temperature sensor in the fiber optics auditorium room. So that's usually how you name a sensor. But when we talk about this global Internet of Things, this naming scheme will fail. Why? Because this sensor may be used for different purpose. Maybe it's also a humidity sensor, and then maybe its location will change. Maybe it will serve for different purposes, different services. So in that case, naming actually becomes much harder than what you think. So that's the first one. And the second one I want to highlight, of course, is the contextual communication, right? So contextual communication is a new thing in Internet of Things. Right now, if you think about all the devices or the sensors, there are too much data generated. And then maybe you only want this data under certain contexts, but how do you implement that? Anyway, so these two are just, I'm going to pick these two to talk about it, to give you an idea that to implement, to realize this Internet of Things picture vision is actually quite hard. Of course, there's mobility. There's also scalability. Everybody talks about scalability. If you have 15 billions of such devices, what do you do with them? And if they report a status every second, how do you deal with such data volume? So all these things are becoming really challenging. And now let's go back to the history, right? So that's the requirements. That's the nice picture we want to have. But what did we have? So if we go back to look at the legacy IoT system, if we go back to way back, IoT always started with these vertical silos. So what do we mean? That means if you want to get some data, you need to start with deploying sensors. You deploy the sensors, you have all these IoT devices, then you deploy the IoT gateway. Then on top of that, you deploy a separate IoT server, and on top of that, you deploy the application. And all these silos that actually could be using proprietary communication protocol. What does that mean? That means they do not really interoperate with each other. They can't use each other's data. And if you want to have a different application, then you need to deploy a different silo. So of course, that's given the internet. I mean, these silos actually existed before the existence of internet. And right now, internet is interconnecting everything. Of course, this is really not efficient. So what is the new trend? The state of the art in terms of globalized Internet of Things is to, instead of having proprietary communication protocols between IoT devices and the gateway, why don't we use generalized API? So how about we develop common API so that all the devices, they can talk to the gateway using the same API, same protocol, and then all the data are going to be collected by a centralized IoT server, so that if I want to use some data from Japan, I can just go to this IoT server and get it. Of course, so this is what is happening. There are a few initiatives in Europe and a few in the United States, and they're all doing this overlay-based IoT service. But we actually think this is not enough. Reason being, this overlay is definitely built upon the current internet. And the current internet, as we know, well, this is a future internet lab, so we know it does have several problems. So these are typical problems that the current internet have. Mainly, it's not designed with this scale, the mobility pattern, the communication pattern, the contextual communication, all these characteristics in mind. So what we are thinking is, why do not we actually build a platform that supports IoT using ICN, Information-Centric Network? So what's the difference? If you look at this picture, compare this with the previous picture, they look awfully the same, very similar, but with a huge difference. Difference is, the previous picture we have IP routers, and here we have ICN routers. So what is the difference there? ICN routers, of course, can support cache storage and computing. So it actually has much more functionality when in the network than on top of the network. And also, on top of these internet ICN network, then you still see the overlay boxes. But those boxes are only for administration purposes, so that's only for control purpose. All the data right now exists within the network. That don't need to be uploaded to a centralized server or anything. That could be totally distributed. And then publishing of the data and the discovery of the data and the service becomes much more efficient because of support of ICN. So because of that, of course, I don't want to bore you guys with the benefits of ICN. I mean, we have had several IAB sessions on future internet, and everybody already is very familiar with that. So I'm going to directly jump to, so what is the architecture design of ICN and IoT? So if you look at that, the stack, of course, starts with GNRS, which is a name resolution service. On top of that, you have routing. It's very typical. I'm using MobilityFirst as an example, of course. And then on top of that, you have transport. Then you have name assignment service. So this is very standard stuff. But if you look at the middleware services that are supported on MobilityFirst, so this is very IoT centric. You are going to have discovery service, publishing, discovery. This is critical to IoT, central to IoT. Then you are going to have data analysis, event detection, contextual reasoning, and security privacy, of course. Then I'm going to also provide you a very brief example just to show you how things work. Right, so you could have all these small local IoT networks. Those are just sensor networks or things like that. And each sensor can have a GUID. Or if sensors data item is important, each data item can have a GUID. But of course, we do not encourage that. That will really worsen the scalability issue. And all these the sensor IDs and the sensor GUIDs and the content GUIDs will be pushed to the ICN network, okay? And it will be, this publish and the discovery will be done through the IoT namespace, which, as I have said, is only a namespace. It's only for administration purpose. It actually does not deal with data. And the data, its publishing and the discovery will be done within the network itself. So that's the main difference between this solution and the current overlay-based solution. So after we look at the architecture design, I'm going to then walk you through a simulation study that we conducted. And through this simulation study, you will see more clearly how this ICN-based IoT can be implemented. So here we are going to look at two specific examples. One is NDN. What happens if we use NDN to support IoT? And what happens if we use MF to support IoT? And we did compare these two things using some performance metrics. But I just want to say, don't read too much into this, because we did not really build an integrated simulator that implements both NDN and MF. We actually used separate simulators, each from their own research group. So the comparison is mainly just for conceptual comparison purpose. Of course, everybody knows what NDN is. If you want to get something, you send out an interest, and the service provider or the data provider is going to respond to your interest with the data. And then on each router, so this is NDN's major weakness. On each router, it maintains forwarding information base, pending interest table, and a content store. So it's pretty cumbersome. Then this is the MobilityFirst overview. Of course, everybody is super familiar with that. In the context of IoT, you know, each content, each sensor could have a dual ID, and we track their locations through GNRS. And because we are supporting Internet of Things, we actually need to create different types of dual IDs, as I will mention just in a little bit. All right, so first thing is device discovery. So this is not even data discovery. This is what happens when you add a new IoT device to the network. So as far as NDN is concerned, you know, NDN naming for IoT is actually based upon the well-known manufacturer ID and a self-certifying name. So I just want to actually only emphasize one thing. Then if you are using NDN IoT, so this protocol is not designed by us. Actually, this is designed by NDN group. So if you are using NDN to support IoT, as soon as you have a new sensor to the system, the sensor actually remains passive until, but what all the applications are doing is going to periodically send out interest messages. All right. If a sensor's data is not interested to anybody, this sensor's data will remain unseen. Well, that makes a lot of sense. So the applications are going to periodically send out different interests according to their needs, and this new sensor, if sees the interest actually fits their profile, is going to respond. So this is how device discovery done at NDN. So as far as MobilityFirst is concerned, it's more, how do I say it, active. That means because MobilityFirst does not have this concept of interests. So as soon as you add a new sensor, so this sensor will be assigned to a GUID. In this case, we call it 1, 2, 3, 4, 5. And then it will be inserted into the GNRS table. And actually, which GNRS table? It will be inserted into two separate GNRS tables at least. One is what we call service. Based upon which service this sensor provides, this sensor will be merged into the service group, because there could be several temperature sensors. So this 1, 2, 3, 4, 5 will be one of them. And within MobilityFirst, we do have service GUID. So each type of service also has a separate GUID. Besides that, this new sensor's GUID will also be inserted into this device that's attached to a router or sink, depending upon your terminology. So that when the service GUID is for service discovery, and this router GUID is for physical forwarding. All right, now let's look at the first step is the device discovery. The second step is how is the data publishing and the subscription is done. For this NDN version, there's not too much I can say, because they used the proprietary content-oriented PubSub system that if you're interested, I can point you to the reference on this. But MobilityFirst is actually pretty interesting. So after this sensor is inserted into the system, we also create a subscription GUID. That is, subscription GUID connects all the data source, the providers for certain data, as well as the subscribers for certain data. So because of this, we have subscription GUID, then you are going to have a larger mapping table, which for each subscription GUID, you map to the source and the destination. And if you look at this rider on the right, it says, okay, I know something about a subscription 456. And actually, among all the sensors that are attached to me, sensor 789, among all the applications that are attached to me, application 789 specifically subscribed to this particular subscription. So this is how, because of all these mapping table, then the right information will be pushed to the right subscribers. So this is how MobilityFirst implements data subscription and the publishing. Now, after we talk about the details, we actually looked at 2 use cases in this simulation-based study. One is what we call it. So both use cases are in the family of smart campus. The first one is a stationary IoT scenario called a building management system. Because NDN is not really tailored for mobile cases, we think it will be unfair if we just look at the mobile situation. So we start with a stationary IoT, it's a building management system. And the second thing we want to see is a dynamic case, because IoT will have a lot of dynamic use cases. It's unavoidable at a school bus system. So if this is how a building management system looks like, all these different sensors attached to sinks. And this is our simulation setup. We considered a bunch of sinks. Each sink is each sink actually is attached by a few sensors. And then, as I have said, this is only simulation comparison. And the simulators are not an integrated one. It's actually coming from 2 separate implementations. So I don't really, I'm a performance evaluator by training, so I'm a little bit nervous when I present these results. But it gives us some insights, all right? The first thing it says actually in a stationary case, actually, MobilityFirst only performs slightly worse than NDN. That's actually a big deal, because every time when we submit a paper about MobilityFirst, the first question we always get is, well, are you guys mobility first or mobility only? Because our protocols are actually mobility friendly, and a lot of times in stationary cases, we may not fare as well as the other alternatives. But if you look at here, the delay is just slightly worse. But our advantage will show really clearly in picture 3. This is the control overhead, the footprint on each rider. Because as I have said earlier, NDN does maintain a very complex data structure. And because of that, if you look at the red bar, so all these table sizes are much larger than the state information MobilityFirst maintains. And the good put, I wouldn't read too much, because the good put, MobilityFirst is much larger because our PDU is much larger than this specific implementation of NDN. But I think the lesson here is, in stationary case, and MobilityFirst didn't perform much worse than NDN with much less control overhead. And in the school bus situation, of course, this is our strength. And so the situation we consider is we are going to have sensors on each school bus, and periodically they send out information. And the sync in this case is actually stationary, because each bus is sending information to their centralized server. But you can easily imagine that this can be extended to a mobile sync situation as well. What if the students who are viewing the bus information on their smartphone? So if you look at that again, I think in this here, our speed, the packet success rate for MobilityFirst is actually better, all right? But if you look at the control overhead, the number of packets that are pumped into the network, MobilityFirst is much smaller. Question?
Say again, you're comparing MobilityFirst against what?
Oh, the first one?
What you're comparing? MobilityFirst and?
NDN.
What is NDN once again?
Oh, sorry. So NDN stands for Named Data Network. So it's a content-centric content-centric future internet architecture. So NDN actually has already implemented a campus-wide prototype to implement IoT.
So can you explain why in the stationary case is worse? You said why. Do you have explanation?
Oh yes, we do. But that explanation is not to be generalized across the architecture. The reason is in this specific implementation of NDN, their implementation is very simple. They're only targeted at this specific building management system. However, in our implementation of MF, we were trying to be really generic. We considered mobility, we considered different mobility speeds. Because of that, our protocol overhead, we do too much processing on each node compared to what NDN, the simulator, does. Because of that, our latency is actually slightly higher due to this processing overhead. So that's what I'm saying. I'm trying to use this comparison study just to show how NDN IoT and MF IoT can be implemented instead of looking at the results, just because it's really too specific to the simulator implementation.
So can you explain how packet success rate is measured? I did not get the connection between whether it's MobilityFirst or NDN. Why is the packet success rate different?
Okay, so packet success rate, let's say if it's NDN, if you, and the centralized server is going to push interests out, and the sensor will see the interest and respond to the interest by the data. But the sensor is on a mobile device. In this case, it's a bus. So maybe the connection is already lost or things like that. Because of that, so NDN has to rebroadcast their interest. So that's why the packet success rate for NDN will be worse.
So what does MobilityFirst do?
So MobilityFirst, actually, it's the blue line in the packet success rate. If the speed is moderate, it's actually much better. When the speed is really, really high, I think it's a saturated case. We shouldn't really look at that range. I should have talked about.
The packet success rate is better because you're accounting for mobility somehow.
Right. Okay, so this is the simulation study. In the third stage, I also want to just, I'm going to be 1 minute over time. Just a couple of prototype systems we have at WINLAB that implements IoT. So we have our IO system, which is IoT system. So we implement this Marauders map, which keeps track of the status of different parts of the building, and it keeps track of different items. And it also gives you status. It detects whether the door is open when it shouldn't be. It detects whether some place has water when it shouldn't be. If that's detected, it's going to alert you. So that's the system we have. We have also deployed this system to monitor animal conditions in animal labs. At the same time, we are right now in the situation of pushing MobilityFirst to support all these IoT. So this is a simple demo that we have. In this demo, we have sensors at WINLAB. We are using a smartphone as a IoT gateway which runs MF stack. So you can actually have several mobile devices that can communicate to each other. They can look at the sensor status through MobilityFirst network. And right now, so these are two parallel initiatives. One is the OWL, which is a pure sensor network based upon IP. The other is this new architecture using MobilityFirst. So right now we are in the process of combining these two to push MobilityFirst to support much larger IoT system that's currently being supported by OWL. All right, so that is the status report from WINLAB on the IoT initiative. Any questions?